Thank you, Alessandro. This is an excellent time to get into machine learning, especially on microcontrollers. Many industry reports talk about how the Internet of Things is just about to explode, with literally trillions of connected devices. And this is echoed right now by the growth that we're seeing in Cortex-M based devices shipping today. This technology will be seamlessly embedded in our cities, our cars, our homes, our factories, and all parts of our infrastructure. And these devices, they're going to scale from the tiniest of sensors up to highly integrated SoCs. So, to understand machine learning as it is applied to microcontrollers, it's important to see it in context. So, machine learning is a part of the broader discipline of artificial intelligence, and there are many different approaches to machine learning, right down to very simple statistical techniques. And from one perspective, neural networks are just another technique, a technique in which you train the data to build up these weights in your network, and then at inference time you give it new data, and it just executes those trained weights. However, not only are neural networks redefining the state of the art in field after field after field, they've reached that tipping point of becoming popular enough to get really optimized software and even hardware dedicated to them. Everything from ARM's machine learning processor to upcoming vector instructions in the CPU. And so we expect neural networks to become a standard part of application development throughout the stack. This growth in machine learning powered devices is really being caused by a move from the data center to the edge. This is because data is heavy and moving it is harder and more expensive than running compute. And that's true over several different dimensions. In terms of bandwidth, if you imagine a smart doorbell with a camera that announces like known guests and pets and packages, so transmitting live HD video feeds from hundreds of millions of smart doorbells is a significant cost, right? Both to the consumer, the network provider, and the cloud provider. Now, if that recognition is running on the edge, then that saves all of that bandwidth. And this is just one small use case, right? Devices scale, and centralization does not. And in terms of power, just transmitting data actually uses more power than computing on it, even for quite a significant amount of compute. So always-on and battery-powered devices have a much more competitive profile when they're running machine learning on device than if they're uploading that unprocessed data to the cloud. And this cost saving also works out at the other side of the picture. So for device manufacturers, it's a lot cheaper to do that computation on the edge rather than in cloud on servers. Just the complexity and the cost of running a high availability secure cloud service can be a significant competitive disadvantage. But from the consumer's point of view, and the device point of view, if you like, these are increasingly interacting with the real physical world. And in the physical world, latency is everything. And that's kind of why our brains are right next to our eyes and ears instead of being packaged safely away inside our chests somewhere. Time-critical applications, such as automotive, just can't rely on connectivity in the cloud. If you imagine at highway speeds, a car might have traveled 10 meters before a message even completed one round trip. And this is even more true of reliability. We all experience times when our mobile loses its signal, or when the internet just seems to stop working. But machine learning can only become more deeply embedded in devices and in our lives if it's completely reliable. Nobody wants to be locked out of their home because their smart door lost its Wi-Fi signal. And this brings us to the same idea of security and privacy of that data. Collecting massive amounts of data from trillions of devices would just be a terrible idea, both from security and privacy perspectives. Securing internet-connected devices is hard. The safest data is data that's never recorded or sent in the first place. So AI that's in your hands is more responsive, reliable, secure, and your data is better protected because it never has to leave that device, and that means you control it. So to understand this full spectrum of the machine learning deployments, just look at the range of use cases here, from autonomous driving systems down to smart cameras and keyword detection. Now, you need high-powered GPUs or dedicated devices to train a neural network, but not to execute one. In fact, Facebook's recent paper, Understanding Inference at the Edge, showed the vast majority of Facebook's on-device workloads today, they're running on the CPU. And in fact, over 90% of the AI-enabled units being shipped today are based on the ARM architecture. Now, some of the most interesting machine learning deployments are down at this lower end of the ubiquitous, low-cost, low-powered, always-on, kind of always-aware spectrum, sometimes referred to as voice, vision, and vibration processing, covering everything from cameras that detect if an old person has fallen to machines that can predict when their own parts are about to fail. This is the area that we're going to look at today, and Alessandro is going to show how this can be done in practice. So over to you, Alessandro.